Okay, I promised we'd come back to Mr. Bernoulli and his principle that I don't really like, but here we go. Bernoulli's principle. If you want to know a little bit more about what the FAA has to say about it, you can go to Fact Chapter 4. It's in there somewhere, point 6 or something. They have a small little thing on there. And if you actually open up the FAQ and you do look, or you get online and you look at what they have to say about Bernoulli's principle, you'll see this funny little diagram. It'll look like this. This is how you know you got to the right spot. So you have this pipe, or this tube here, and it comes down into a smaller pipe or tube, and then it gets bigger again. And they show there's some fluid or water or gas going into the tube and out of the tube. And what they're trying to show you is they have these little pressure readers here showing you PSI or whatever. And what they're trying to tell you is that there is a pressure right here, and the speed is, I think there's pressure and speed on these things, but we'll just show you here. Pressure's there, pressure's there, pressure's there. Okay, so what's showing you is that the pressure is lower here, but it's telling you that the speed, we'll do this here, speed, velocity, the all fancy velocity and pressure, velocity and pressure. So the pressure went down here, and it's higher here, but the velocity is lower and the velocity is higher. Velocity is lower. Okay, so what is Bernoulli's principle? That as something is moving slower, it's going to have a higher pressure. When it's moving faster, it'll have a lower pressure. And then here you see it's moving slower and having a higher pressure again. So what does that all mean, and why is there showing a picture of a tube here? It's confusing. The best way I like to describe this, before I get too far, is I like to think about basic physics principles. So there's this principle in physics, which in my opinion sums this up a lot better. And it talks about the conservation of energy. So what that's saying is, let's pretend you're a human being, because you are a human being, and you only have so much energy in you. And there's only so much energy in the world. And there's only so much energy that if I drop this marker, it's going to hit the ground. That's potential energy, right? It's not the same amount of energy as if it were up higher or lower. This is how much energy there is, right? Okay, so what's going to happen with the energy? Well, we use the energy, and then it goes into something else. So I take some food, and it's cold, and I put it in the microwave, and I turn the microwave on. So the microwave creates energy, and it loses the energy because then it goes into the food. So the energy doesn't disappear, it goes someplace. I guess that's the point. The energy never disappears. It always goes someplace. So the conservation of energy is going to say that there's only so much energy in here. It's not being added. It's not being subtracted. It's just going in different directions. So with that, there's a thing called static pressure, and there's a thing called dynamic pressure. So dynamic pressure, let's get a different mark here. Dynamic pressure, dynamic, is going to be this force, this energy that's moving this direction. Okay? The static pressure is the energy that's just pushing out generally. So if there's water running through this tube, and there's water molecules in here, let's say, okay? Each molecule has, let's say, 1 unit of energy. Whatever that unit is, who cares? 1 unit. Actually, let's make it 4 units. It makes it simpler to explain. Here's our one little water molecule. And let's say it has 4 units of energy. So we'll say 1 unit's going up, 1's going down, 1's going forward, 1's going backward. Okay? 1 unit of energy, you have 1 unit going each direction. And so that means we're assuming that this water molecule is just hanging out in a swimming pool or just stagnant in here, it's not moving. But then what happens, this is our static, technically. This is all static, it's just sitting there. Okay, what happens though when we start adding dynamic energy? That is when this conservation of energy principle is important, and that's why Bernoulli is important. So what happens is, are these little molecules, let's say this is just cut off, they're just sitting in this bottle. They all have 4 units of energy and they're all just floating around. Okay? So that means they each have 1 unit of energy pressing up this way, 1 unit pressing that way, this way, that way. Okay, now let's open this up. Let's open this little hole. It's open now. And they're going to swoosh this way. Well, that's called our dynamic energy. It's moving forward. Okay? So now we're going to have, let's say, 3 units of energy going forward. 3 units of energy going forward. We're only left with 1 more unit. So we're going to have 1/2 a unit going up and 1/2 a unit going down. So what does that all mean? What that means is that our dynamic energy has increased. So our static energy, the energy that's pushing up on the pipe, has decreased. So what does that mean? That means as it goes into this tube, it's going to go faster. That faster is our dynamic energy. The more pressure that's pushing forward, the less can push on the pipe. Again, the more of the energy, the more of the pressure that's going forward, there's less energy left over to push down and out and about in other directions, okay? So that is why here we're saying this is a very low velocity, so there's not as much dynamic pressure. That means there's more energy, more pressure that's able to press on this surface here of this pipe. When it gets smaller, this is like a little venturi, you go smaller, it's going to speed up to get through there. Okay, that's a different principle, but so when you get through this venturi here, it has to speed up to get through there. With the extra dynamic pressure going forward, it doesn't have as much pressure left to press on the walls. A way you can explain this is if I'm standing here and I'm not going anywhere, I could lean against this wall and put all my weight on it. I could push all my energy into this wall. But as soon as I start moving forward, I'm not going to be able to press as much of my weight on my wall because I'm too busy moving forward. So as the fluid is moving faster, that doesn't mean it actually has less pressure. So this is kind of deceiving. It has the same amount of pressure. The difference is that it's not pressing down, it's pressing forward. So it's not, having more static, it's having less static pressure. Why does this have to do with flying? Well, this has to do with the principle of lift. So we have our airfoil here. And this is what I don't like about Bernoulli and flying. So there's this idea that because of this magical shape, and we talked about this before with the air molecules, right? We have our air molecules. This is going to attack the air molecules going forward. More of them are going to be down here, and they're going to separate, and less of them will be up here. Okay, that's understandable. So what does Bernoulli have to do with this? There's a theory, and the old thing that they used to tell students, which turns out not to be true at all, so I don't even know why they said it, is that because there's more surface area on the top, if I were to measure this, it would be longer, bigger, more surface area than this. This is a straight line. This is a out of the way around the neighborhood scenic route. Since this is a longer distance, these molecules would have to travel faster than these molecules to meet up at the end. So the old idea was they have to meet up at the end. They separate and they have to meet up at the end. There's no reason they have to meet up at the end. They don't meet up at the end. There's no reason to say that. So it's completely out of the way. So why did they say it goes faster? I don't know. No one's explained it to me. Supposedly, these molecules, because of the shape of the airfoil, for whatever reason, supposedly move faster. You could think of it maybe as a slide. You could also think of it as maybe this low pressure system is sucking the molecules back. That could be why. That could be the real reason why. It doesn't matter why. We don't know why. Who knows? I'm not, the engineer. But whatever the case is, supposedly these molecules move faster than these molecules. Okay, so as long as we can agree that we may not know exactly why that happens or why it's necessary, it doesn't really matter. These move faster, these move slower. They all have the same amount of energy and pressure to start. So Bernoulli is saying these molecules moving across the top are using more of their pressure and energy in dynamic energy. So this dynamic energy moving faster, okay, is pressing less on the airfoil. If it's pressing less on the airfoil, it has lower pressure. These are moving slower, like little slow pokes, so they have more energy and more pressure left over to press more on the airfoil from the bottom. So, the exact same principle as before. The only difference is, instead of the shape causing the molecules to spread out, what we're saying is that for some unknown reason, molecules want to go faster over the top of this airfoil shape. They want to move faster. Whereas on the bottom, they move slower. The slower movement will have a higher static pressure and a lower dynamic pressure. The ones over the top will have a faster speed, a more, higher velocity, so they will have more dynamic pressure, which takes away from the ability for the static pressure. So maybe there really is a good reason. Somebody could tell me. I would love to know. As far as physics is concerned, I don't know why an air molecule would want to move faster because they're going over a fake hill. Maybe that's all. They just like to go down slides. So whatever the case is, Bernoulli's principle says that the molecules go faster over the top of the airfoil. Moving faster means less pressure. That's all you need to know. Moving faster, less pressure. Moving slower, more pressure. So as you can see here, that's the reason. I wanted to show you the conservation of energy and the dynamic versus static as to why that makes sense, because this up here, to me, really has nothing to do with flying, but it may make perfect sense to you. But hopefully this kind of helps, and if someone tries to tell you that these guys are running a race and they have to meet up at the end, that's not true, but you could just nod and smile anyways. Alright, so hopefully you understand why I don't really like Bernoulli, but I hope you understand what Bernoulli's trying to tell us and what it has to do with flying.